In this video, we're going to set out to show that matrix transformations are in fact linear transformations. So suppose we define a transformation as follows. T of x, so this transformation, this function called t, is going to input a vector we'll refer to as vector x, and its output will be the product of some matrix and that corresponding vector. So to give these dimensions, we'll say that A is some m by n matrix, and x is therefore some n by 1 vector, giving us an answer that will be m by 1. Our dimensions here of this vector will be m by 1. Inner dimensions match. In other words, let's suppose we have a matrix transformation, which this matrix is going to take some vector and potentially move it in the same dimension or transform it into another dimension. So it could be from R2 to R2, it could be from R2 to R3, it could be from R5 down to R4, many different possibilities. In order to show that this is a linear transformation and why this is important, we have to recall the two properties that a linear transformation must obey. It has to obey both of them. If you take a vector and you scale it first and then transform it, you should get the same answer as if you transform the vector first and then scale it. Also, if you add together two vectors and then transform the resultant vector, you should get the same answer, the same vector, as if you transform each of the vectors first individually and then add them together. Now these linearity properties we've kind of described as distribution in a way, though remember that t of x plus y is, t is not multiplying, it's a function name and it inputs the vector sum x plus y. Now, in order to see that this is a linear transformation, we will use a couple of matrix arithmetic properties. If A is an m by n matrix, u and v are vectors in Rn, and C is a scalar, then if you multiply the sum of two matrices by a matrix, you can actually distribute that matrix in. Now, this is a property of multiplication here. Up here, notice that this is not t times x plus y, so it's not that we're really distributing it, but notice that property 2 and property A look very similar in a way. Also, if you scale a vector first and then multiply it by a matrix, you get the same answer as if you multiply the vector by the matrix first and then scale that result. So this will not be too hard to show that matrix multiplication is in fact a linear transformation. So let's show that the left-hand side equals the right-hand side of property A. So if we take the transformation of C times X, what does this mean? Well, this means that we're going to input C times X, and C times X is going to get multiplied by A. So by definition of our transformation up here, T of X equals A times X, this is going to be equal to A times the input, which is C times X. Okay, now we also know, now that we can use the property B, we know that we can factor that constant out and write this as C times A times X. Now let's show that in fact that's going to give us the same answer as C times T of X, that this is the right-hand side we're now going to expand upon. So we're going to take C times the transformation of X. Well, what does that mean? Well, that means that T of X is equal to, T of an input is equal to A times that input. In this case, our input is just the vector X, and you can already see that these are equal. So property 1 holds, and now property 2, we need to show that if we transform the sum of two vectors, that we get the same answer as if we transform X, then we transform y, and finally we add them together. So let's do the left-hand side. T of x plus y. Well, this means that we're going to take x plus y as our input and multiply it by A, right? Because our transformation is defined as A times the input. Now that this is multiplication, we can use property A to see that this distributes into A times X plus A times Y. Now we haven't shown that it's linear quite yet because we need to show that the right-hand side gives us the same result. Well, T of X is going to be A times X, T of Y is going to be A times Y, and finally we add them together, and once again we can see that these are in fact equal, and therefore a matrix transformation of the form A times X follows and rather obeys the two properties of a linear transformation. Okay, so now let's ask the question, if we have a linear transformation, how do we find a matrix to perform the transformation? We're going to do a quick derivation here just to kind of show where this comes from. We know, first of all, from one of our previous videos, that every vector is a linear combination of the standard basis vectors. Okay, what are the standard basis vectors? As a recap, if we're in n dimensions, then it's the collection of vectors where every vector has a 1 in exactly one position and zeros for all of the other entries. So 1, 0, 0, 0, 0, 0, 1, and then a bunch of zeros, 0, 0, 1, a bunch of zeros, etc. until we get to the final vector, which will have zeros all along the top and then a 1 down on the bottom. Okay, these are all n by 1 vectors. For example, in R2, if we want to express the vector x1, x2, so let's say in the xy plane we have some vector, I'll draw it over here, let's say that's the vector with components x1, x2, stated generically. What we can do is we can write this vector as x1, the component, times the 1, 0 vector, plus x2, the component, times the 0, 1 vector. You see that we get the x1, x2 vector. Now another way we could write that, we call this E1, we often call this E2, and so just replacing the vectors with their labels, x1, E1 plus x2, E2. And finally, by kind of undoing matrix vector multiplication, we can see that this is going to be E1 and E2, those as the columns of a matrix, times the components x1, x2, because once again, this component scales this column, this component scales this column, and we get this expression to the left of that equal sign. Now suppose we apply a linear transformation to this vector. Okay, so now assume we have a linear transformation that we're trying to perform, and we're trying to find the matrix that will do that for us. Okay, so in other words, let's say that I have a vector, and what I want to do is perhaps negate both of the components. So in other words, I just want a vector that will get transformed, kind of rotated 180 degrees, and it will become negative x1, negative x2. Now, assuming that that's a linear transformation, if I want to transform the vector x, and I can express the vector x as having the components x1, x2, which can also be written out as the transformation of x1 times the 1, 0 vector plus x2 times the 0, 1 vector. Okay, and I'm just expanding that out a little bit. Now, because we are assuming that we are looking at a linear transformation, that also means that the transformation of a sum of two vectors, think about this as one vector, and think about this as another vector. Since this is a linear transformation, we can apply property 2, namely this guy here, and I can take the transformation of the two vectors separately. The only reason I can do this is because I know that I'm looking at a linear transformation. So if we want to just kind of intuitively think about this as the function distributes to the two vectors, that's okay for now. And now I have a scalar times a vector, and so this was property 2. And by property 1, if I have a scalar times a vector, that I'm transforming, I can actually write this as x1 times the transformation of the 1, 0 vector. And I can do the same thing over here. Okay, now what I'll do is I'll write this out in one final way. I'll write this out as, now this, remember, this is E1 right here. This right here is E1, and this right here is E2. And so what I will do is I will write a matrix, which will be the transformation of the 1, 0 vector, transformation of the 0, 1 vector, times the components x1, x2. So I'm writing this now as matrix vector multiplication. Now if you notice, this right here is a matrix because it has 2 columns, each with 2 values, 2 rows. And so if I think about what's in the box as the matrix A, and x1, x2 is the vector I was trying to transform in the first place, then we can see the correspondence here. The 2 boxes are the same matrix. And so to find the matrix that will perform the linear transformation that I want it to perform, I would write A equals the transformation of E1 and the transformation of E2. So these are separate columns. I'll put these little lines here to indicate that those are going to be the new columns. And what I put in for those columns is the transformation of the E1 vector and the transformation of the E2 vector. Okay, as a brief example, here we said we wanted to negate both of the components. So if I wanted to find the matrix A that when I multiplied it by the x1, x2 vector, what I get as an output is negative x1, negative x2. In order to find what that A matrix should be, all I have to do is transform E1 and transform E2 separately. Now that might seem like a how do you do that kind of task, but if I want to transform E1, remember what that's going to do is transform the 1, 0 vector. Okay, now the 1, 0 vector we know is 1 unit along the x-axis, like this. Say that's the 1, 0 vector. And if I wanted to transform it, in other words, negate both of its components, well, the negation of 1 is negative 1, and the negation of 0 is negative 0. I'll just write a negative 0 there, but 0 is 0. It doesn't matter. And that means that the transformation of that 1, 0 vector is the vector negative 1, 0. And that's my column in the A matrix. Just as simple as that. Now, the transformation of the E2 vector, E2, remember, is the vector 0, 1. And if I apply the transformation to it, in other words, negate both of its components, it's going to become the vector 0 or negative 0 and negative 1, because the transformation just negates both of the components of the input vector. So now I'll put in 0, negative 1, and that is my A matrix. So all I have to worry about is transforming the standard basis vectors, placing them as columns into the A matrix, and now I have a matrix that will do that transformation for me. So let's kind of check our work here. Let's check to see that this is indeed the matrix that will do that. And as an example, let's pick the vector, say, 2, 3 as my input. We'll say x is the vector 2, 3. Now if I take this A matrix that I just built, and I multiply it by the 2, 3 vector, I will get 2 times negative 1, 0 plus 3 times 0, negative 1. This will give me negative 2, 0. This one will give me 0, negative 3. And we do indeed get negative 2, negative 3 as we had desired. So we now know how to build the matrix for a linear transformation. You might ask, well, what if this is not in 2 dimensions? What if it's in 3 dimensions? Well, in general, we would have A consisting of the transformation of each of the standard basis vectors in whatever dimension we start in. So notice here, and we'll see more examples in our next video here, we're just kind of building the concept. I'm going to start off with an n-dimensional vector. My A matrix will contain the transformation applied to each of the basis vectors in n dimensions. Okay, it will have n columns and it will have m rows. We'll see how we can actually toggle between dimensions in a future video. X is an n by 1 vector, and when we multiply these two together, we get an m by 1 vector. In our example up here, we started in R2, and we transformed the vector back into R2, so it was a 2-dimensional vector that when it got transformed was still in 2 dimensions. But this can also apply if you had, let's say, a 3-dimensional vector and you wanted to map it into 5-dimensional space. Now, in graphics, things like that, there's no such thing as visualizing 5 dimensions, arguably. However, when we're dealing with data, there are a lot of instances where we do go from a lower dimension into a higher dimension, and there are also things in data that we do. Like, for example, if you find the average of, let's say, 5 data points, you're going to produce a single number that will represent the average of those 5 data points. So in analyzing data, we often go from dimension to dimension, usually from higher dimensions into lower dimensions, because our brains have a harder time working in those higher dimensions. So what we've just built here is the idea that if we know we have a linear transformation, we can find the matrix by performing the transformation on all of the standard basis vectors, which is usually pretty easy since a standard basis vector has 1, 1 and n-1 zeros in it. It's often not very difficult to build this, which gives us a really fast way to design these transformation matrices.